Welcome, Precalculus students. This is week 3 of distance learning. Last week, we finished up the chapter on polars, and so this week we are starting the new chapter on sequences and series. Today we're going to be looking at two different sections here. We're going to be looking at arithmetic sequences and series and geometric sequences and series. The best way to think about the differences between arithmetic and geometric sequences and series is that you have arithmetic, which is adding or subtracting a number each time. So for instance, 2, 4, 6, 8, 10, 12, or 2, 0, negative 2, negative 4, negative 6. And then you have geometric, which is multiplication each time. Common mistake people make on this is they think multiplication and division. No, it's simply multiplication each time. If you are going down, you are simply multiplying by a fraction. So a sequence of 25, 12.5, 6.25 would end up being multiplied by a half. That's really important because when you see it in the formulas, you're only going to see a multiplication. So up here on the board, what I have written down are the formulas that you're going to need to know when looking at these problems from the text this week. With arithmetic sequences, you're going to see it on the left side of this board. For geometric sequences and series, you're going to see it on the right side of this board. The first formula for each is how to find a specific term. This is very useful if you were, say, finding the 5,000th term of a sequence. You're not going to have to go into your calculator and get plus 2, plus 2, plus 2, plus 2, plus 2, 5,000 times. You simply plug it into this formula. Same thing with geometrics. Times 7, times 7, times 7, times 7. You don't have to do that. You can plug it into the formula. Then the other formulas that are listed there are the sum formulas. The sum formulas are useful when, say, you're taking the sequence 2, 4, 6, 8, 10, and on for 200 terms, and you wanted to find the sum. That might take you a while. But if you used the sum formula, you could calculate it in a matter of less than a minute. So the term formulas for arithmetic. The term formula for arithmetic is a of n equals a1 plus n minus 1 times d. A of n is the term you're looking for. A1 is the first term in the sequence. N is the term you're looking for, so the 50th term of the sequence. 50 would be your n. And then finally, the d is the common difference. It's what's being added or subtracted each time. So in a 2, 4, 6, 8, 10 sequence, 2 would be your common difference. The sum formula for an arithmetic sequence, you have two different ones you can use. So depending on what you're given, you can utilize either one of these two formulas. The first sum formula, the sum of how many ever terms you're looking for, equals the number of terms over 2 times, and then in parentheses, a1, which is your first term, plus an, which is your last term. So if you're given the number of terms, the first term and the last term, this would be your go-to formula. The second sum formula, the sum of the number of terms equals the number of terms over 2 times, and then in parentheses, 2 times a1, so 2 times the first term, plus, and then in parentheses, n minus 1, so the number of terms minus 1, times d, or your common difference. This is a useful formula if you're not given a of n. Now the formulas for the geometric. The term formula, a of n equals a1 times r to the n minus 1 power. The a of n, or the number at that particular term in the sequence, equals a of 1, or your first term in the sequence, times r. R is the common ratio. That is going to be the number that you're multiplying by each time in the sequence. So if you're multiplying by 2 each time, 2 would be your r. If you're halving each time, 1/2 would be your r. to the power of n minus 1, n being the number of terms. The sum for a geometric sequence. The formulas for the sum. S of n, or the sum of so many terms, equals a of 1, or your first term, times, and then in parentheses, on top, 1 minus r to the n. 1 minus your common ratio to the number of terms, divided by 1 minus r, or your common ratio. This is a great formula to use if you're given the first term, the common ratio, and the number of terms. The second formula, S of n, or the sum of the number of terms you're looking for, equals, then on top, a1, or your first term, minus an times r, or the last term times the common ratio, divided by 1 minus r, or your common ratio. And then lastly, we have s. S equals. There's no s of n this time. For this formula, s, that's an infinite sum. There's no number of terms there. It's an infinite sum. And this s equals a1, or the first term, divided by 1 minus r, or your common ratio. Now that we have all the formulas down and some understanding about what each particular letter means, we're going to go ahead and look at some examples dealing with arithmetic first, and then moving to geometric. What you see here are 3 examples dealing with arithmetic sequences. Technically, there are 6 examples, but who's counting? Example number 1, what you see is an arithmetic sequence, negative 29, negative 2, 25, and so on. What we are going to do for this one is we are going to find the explicit form, or our term form. The recursive form, most of you have seen this in the form of now versus next in an Algebra 1 piece, and then the 38th term of that particular sequence. The explicit form is our term form simplified, so we're going to go ahead and write up our term form for this sequence. So an equals a1, or negative 29, plus n minus 1 times our common difference, or d. What you notice each time between negative 29 to negative 2, or negative 2 to 25, we are adding 27 each time. So to finish this explicit form out, what we're going to do is we are going to distribute the 27 to both pieces inside the parentheses, and then combine our 2 numbers. So 27 times n and 27 times negative 1, and then combine the negative 29 and the negative 27. Your explicit formula answer, a of n equals 27n minus 56. The second piece of this example is to find the recursive form. Like I just mentioned, the recursive form is technically a now equals next. So what's happening each time of this sequence? And hopefully you saw from the beginning that we are adding 27 each time. So the recursive form, it's pretty quick and simple, but make sure you understand how I'm writing this up. A of n, or the next term, equals a n minus 1, so the now term, so the a n minus 1 is now, a of n is next, so next equals now, plus 27. It's always going to be, for arithmetic sequences, the recursive will always be a of n minus 1 plus or minus whatever that common difference is equals the a of n. And that's the second part to this example. And then the final part is to find the 38th term of the sequence. Find the 38th term of this sequence, so negative 29 to negative 2 to 25 to the 38th term. To do this, you can do one of two things. You can take 38 and plug it into our n in the first equation that we wrote up, or you could take 38 and plug it into the final answer of the explicit form. If you wanted to plug 38 into the original term formula, I went ahead and put that in, and then all you would do is calculate negative 29 plus, in parentheses, 38 minus 1, or 37, times 27. After you calculate, you should get 970. And that finishes example 1. Example 2, we are going to find what goes in each one of these 6 blanks between our first term of 12.4 and the last term that we're given of negative 24.7. Technically, what we're doing here is finding the 6 arithmetic means between these two numbers. Now, there's 2 ways that you can tackle this problem. One way is you can plug these 2 pieces into your arithmetic term formula and find out what the difference is each time. You can see this done in your textbook in example 4, but I'm going to give you a different way to go through and solve this piece. I take the last term minus the first term and I divide it by the number of blanks plus 1. So negative 24.7 minus 12.4 divided by 6 plus 1, or 7, or negative 5.3. So that means we're going to go down 5.3 for each blank from 12.4 to negative 24.7. So 7.1, 1.8, negative 3.5, negative 8.8, negative 14.1, and then negative 19.4. Now we move to example 3, finding the sums. In part A, it gave us the first term, the last term, but it did not give us the n, or the number of terms. What we have to do is we have to utilize the first term and the last term and our common difference to plug into the term formula to figure out the number of terms that we have between 211 and negative 455. So to find the n, you plug in the last term, or a of n, equals the first term, 211, plus n minus 1 times the common difference. The common difference here from 211 to 193 is a negative 18. It's going down 18 each time. Once you've written that out, you're going to solve for n. So distribute the negative 18 to both terms, and now you can combine the 2 numbers on the right side and then move them over. So negative 455 equals 229 minus 18n. Subtract 229 to the other side. Which makes negative 684. And then divide by negative 18, which would give us 38. So the number of terms to get from 211 to negative 455 is 38 terms. Good news is that's the hardest part of this problem. That is the hardest part, figuring out what the n has to be. That's the hardest part in figuring out this problem, because now we have the n, we have the first term, we have the last term, and we simply plug in. So the sum of the 38 terms equals 38 over 2 times, and then we add the first term and the last term together, 211 and negative 455. So the final answer, the sum, is negative 4,636. I'll give you a moment to write that down, and we're going to move on to part B of the last example, which is finding the sum dealing with a summation symbol. I'm going to erase the part A piece so we have a little bit more room to find this last piece of this example. Part B, dealing with the summation symbol here. We have a summation symbol, and I'm going to go ahead and explain what this means in sequence terms. The first term that we're adding together is actually the 23rd term of the sequence. So you're going from the 23rd term to the 37th term, and you're adding them all together. You're finding that sum. So from the 23rd term in the sequence to the 37th term in the sequence, you're adding them together to find that sum. The first question you might be asking is, how do we find the number of terms between 37 and 23? Or you might be thinking, could we just subtract to figure out the number of terms? Yes and no. We can subtract to figure out the number of terms, but that will always give us one less than the n number. So to figure this problem out, we start with finding the n. We can take the top and subtract the bottom, but we must always add 1 when using problems with summation symbols. So 37 minus 23 plus 1. Next, we need to come up with the first term and the last term. Good news is, we have the first term spot, the 23rd spot, that we can use. They gave us the function next to the summation. So take 23 and plug it into this function. So 2 times 23 plus 3. That will give us the first term. And then we will do the same thing with 37. 2 times 37 plus 3 will give us the last term. So the first piece that we're using, the 23rd term, is 49, and the last number that we're using, the 37th term, is 77. Which means we can plug it into the formula and figure out the answer. The answer is 945. That finishes the examples on arithmetic sequences. So now we're going to switch gears and go into the geometric sequences. Now let's look at the geometric examples. Examples 4, 5, and 6. With example 4, very similar to example 1, we are going to find the explicit, recursive, and the ninth term in the sequence. When finding the explicit form, we're going to use our term formula. If you look at what's happening, 4 times a number gives you 14, times that same number would give you 49. So what we're multiplying each time. If you can't see it right away, what I usually do is I take the second number divided by the first number. So I take 14 over 4 to the n minus 1 power. So 4 times to the 3.5 to the n minus 1 power. The recursive form, just like what we talked about with the arithmetic sequences, now equals next, or a of n minus 1 equals a of n. So in this case, we're multiplying by 3.5 each time. So a of n minus 1 times 3.5 equals a of n. And then finally, we're going to figure out the ninth term in the sequence, so we're simply going to plug 9 into our explicit form. which would give us 90,075. And that would be the ninth term of the sequence. And that finishes example 4. Example 5, just like in the last set of examples, this is going to be the geometric means. So you have 2 geometric means in between this set of numbers. There are 2 ways to figure this out. Example 5 in your textbook can give you one way, and then I'm going to show you a different way to solve example 5. The way that I like to solve geometric mean problems is I take the last number divided by the first number, and then I take it to the root of the number of means plus 1. So 13.5 divided by -4 to the third root, which would give us -1.5. So that's the number that we're multiplying by each time in this sequence. So -4 times -1.5 is a positive 6. 6 times -1.5 is -9. And then -9 times -1.5 is 13.5. And then finally, example 6, finding the sum. So A, B, and C, we're going to go through and try to find the sum. In part A, the first term is 8, the last term is 131,072, and the R is 4. So since we have A1, AN, and R, we would use the second sum formula for geometric sequences because we have everything we need to simply plug it in. So in this case, A1, or -8, minus AN times R, so 131,072 times 4, over 1 minus R, or 1 minus 4. So the sum is 174,765. Now let's look at example 2 dealing with summations. So for this particular example, you could use either one of these 2 summation formulas. For this example, let's use the first one since we used the other in the last example. A of 1 is simply plugging in your bottom number, so 0.5 times 2 to the 16 minus 1 power. Then for your R's, you're going to plug in your base, which is 2, for both of those because we're multiplying by 2 each time. And then for the N, you're going to do the same thing that we did in the arithmetics where we take 31 minus 16 plus 1. To get the first term, plug in 16 to the exponents, so 0.5 times 2 to the 16 minus 1 power, which is 16,384. And then if you plug those into your calculator, you're going to end up getting 1,073,725,440. And that's your sum. Now let's look at part C. This is an infinite sum, so we're going to be using the last formula that we have under geometric sequences and series. A1, which is 10 over 1 minus R, so what we're multiplying by in this case, so 10 to -5. R in this case, what we're multiplying by to go from 10 to -5. Or -1/2. 10 over 1.5, or you could say 20 over 3. Or you could say the decimal answer of 6.67. And that finishes up the last example for sequences and series for this week. Now what you're going to see is posted below is the assignment for this week, dealing with arithmetic sequences and geometric sequences. Of course, if you have questions, please feel free to reply, post, chat, or email me. Let me know. Other than that, I hope you guys have a great week. I'm going to be continuing to pray for each and every one of you guys, and I hope to see you guys soon.